Hey George, this is Colin. Gonna be a bit of a curveball for you this time. Instead of making my question, at least this part of my question, just trying to type it all in text, I decided to make a video because it's going to be a lot harder for me to write this specific question up, and I think it's going to be a lot easier for me to communicate, I guess, the few problems I'm having with the cathode design as I've been going back and forth with you on. So I figured I'd make a video. You get to see me wave hands a lot and then kind of talk through it. You can visually see what I'm doing, and would love to give you your 2 cents on maybe some things I'm doing right or wrong, because it's not quite working out the way I've seen it in other white papers I've seen on the topic. So I figured I'll delegate it to the guy who, is basically studying this for his PhD and see if he knows anything about this or what I'm running into. So as you know, I'm just trying to design hollow cathode. As you can see right here, I'll take away from the cross-section view. Here's the hollow cathode. It's mounted on this big aluminum plate back here. To give you some context, the actual use case application that I'm designing it for, again, this is just stuff I'm doing for free time, is going to be on kind of a CubeSat. So the Hall effect thruster, which will eventually be put into, is right here. It sits on top of a pressure vessel, which I've designed. For reasons regarding the CubeSat stamper, the pressure vessel has to be made out of aluminum. So the cathode is going to be mounted on top of this aluminum plate, which is why I model it on this big, square that you uncharacteristically see sticking out of this cathode. So that gives you some context about why that's being modeled for this particular subassembly. So running the thermal design, again, what I'm basing at least the thermal studies on, is the Gracilla paper that you told me about. As you remember, we tried implementing it. We were running a few problems. So I decided, because Gracilla actually, in his white paper, and I'll scroll to it right here. Where is it? There we go. Yeah, actually gives an example hollow cathode setup with dimensions that are actually pretty close to what I need for this setup. So I figured, okay, instead of trying to reinvent his wheel, I'm just going to take the wheel that he speculated will work with all the dimensions, make the actual CAD design, the model of it, and then see if we can actually make it, manufacture it, lab test it, and then we can use it as another interesting white paper to see how well his model works on hollow cathodes. So again, just kind of the main parameters to pay attention to. The insert temperature that he was aiming for was 1310 degrees Kelvin. So that's what I'm aiming to have for this simulation. I'm aiming for the plasma once the coil, the wire heats up the thermionic insert and starts emitting electrons and creates the plasma. This model, if my understanding is correct, tells me the power output of the plasma into the cathode when it's running in self-sustaining mode. So I think that might be one premise that might, again, I have to have you vet me, get your feedback on, make sure this is what this paper is addressing. But if that is what this paper is going over, at the very end, he actually gives a nice little picture showing, okay, for a cathode that's putting out 1 amp of discharge current from the Richardson-Dushman equations that you would derive. It looks like there's about 5 watts between an electron and ion bombardment of the insert being deposited here from the plasma once the plasma is ignited, and then about 6 watts on the orifice being deposited. So that's the input I'm putting into this thermal model that you see here in SolidWorks, which I'll show off in a second, at least the results from me running it. I'll just quickly point out. So the heat power into kind of this center area in this insert I have is 5.5 watts, again, from the previous diagram, 1.3 plus 1.2. And then the orifice, 5.5 plus 0.05, 6. I have that being inputted right over here. And then we get these results popping out. And as you're seeing from the temperature gradient here, 451 degrees Celsius is not quite 1310 degrees Kelvin. So I'm figuring it's something with my setup. So I'd love to give your intuition about what's going on here. Or maybe something is wrong with the model, but I highly doubt that, because he's the one with working on the PhD and I'm still working on my undergrad. So here's kind of the setup. So here, again, this is self-sustained plasma. In terms of how the heat's being dissipated, I have the radiation, and I'll hide this so I can show you my step. I have the radiation being dissipated off of the face of the plate that the cathode's mounted onto, and then just the keeper component here. And I have it radiating. This is mostly just kind of the radiation parameters I have for this setup is in a vacuum chamber, so going to be around, I'm assuming 15 degrees Celsius. Is not going to be in the vacuum of space, because my reading of the literature, and you can correct me if I'm wrong, is that the environment that it's going to be on Earth is going to be a lot harsher for the cathode than it is in space, because it's actually going to be able to dissipate a lot more heat from not having to, or it's basically a lot less likely to fail because you have a bigger temperature gradient basically between the cathode and the vacuum of space, which is close to it's a lot colder than basically 15 degrees Celsius. So this is why I set it up with these parameters. So maybe that's one area that my the simulation isn't quite right. Maybe you can speak to that a bit. The emissivity, I got that again from I think just calculating the emissivity of graphite online, just looking online for that. Maybe that'll be a different parameter. Troubleshoot there. Again, the heat powers from the Gracillo paper. And then all the component contacts, basically whenever there was a connection point between two interfaces, I just treat that as a bonded connection. The one exception I will point out, and maybe this is another area that could use some troubleshooting, although in the Gracillo paper that doesn't really talk about implementing this, is the tantalum foil that you told me to implement in my simulation. I have it modeled as it's technically insular. I wasn't quite sure how to model this in SolidWorks. So what I ended up doing is modeling a thermal resistance interface between the foil and the wires. And then I just looked up online really quick to see what the thermal conductivity of tantalum is. And then, of course, the inverse of conductivity is resistivity. So I just put that in, or took the reciprocal of that, got this number, distributed over the whole thing. I also tried modeling it as insulated before, but when I ran that simulation gave me negative, or it gave me basically that the foil was at absolute zero, which didn't make any sense. So I decided to model as a thermal resistance, but that might be another area where this simulation might not be the best. But yeah, that's kind of the setup. But yeah, that's basically the setup I have. I'd love your 2 cents on what might be going wrong, because again, the results, 500 degrees Celsius or 450 degrees Celsius does not seem high. Yeah, I think that's basically, I think, enough of me rambling for about 10 minutes. Hopefully you got some insight here. Thank you very much in advance. Yeah, take as much time as you need. I look forward to the response you have for this.